Good morning, sir.
Good morning, sir.
Morning, sir.
Good morning, everyone. So, my name is Srikanth. I have done my integrated MSc in chemistry from NIT Rourkela, and I have a good experience in teaching chemistry for the competitive exams like NEET, JEE Mains, Advanced as well. Okay. So, since this is the first class, I have just given my short introduction to you, and I just want to know how many of you have attempted the NEET exam previously. You can just raise your hand. It's very good. I can see a lot of hands raised. And can anyone, if you want to share something with the experience, like how the exam went and what type of difficulties you have faced, you are openly free to say that. Anyone? Or what kind of difficulties you have faced in the preparation, or where you have to improve yourself, such kind of things. I'm not going to ask scores. You don't need to worry. Yes, Harishri, Vaishnavi, you want to say something?
Yes, sir.
Yes, please.
Sir, there is difficulty in inorganic, like remembering all the points.
Okay.
There I would miss, sir.
Okay.
And even organic, some reactions.
Some reactions. Okay, fine. So, any other difficulty, students? You can just share your thoughts. That's it.
So
Because
numericals and physical chemistry in solid states and
difficult or easy?
no, it's difficult for me.
It's difficult. Okay. So, okay, fine, students. Some are saying inorganic and organic. Some are saying physical. That's fine. So, what we are going to do in our course of reaction is we won't just remember the stuff. The first point is we need to understand the thing, understand the concept and apply it. If you talk about organic reactions, it's not like a substrate converting into reactant under some set of conditions. It's more about how the conversion happens, the mechanistic approach. Okay, we are going to study in detail the mechanistic approaches as far as organic chemistry we have been dealing with. Obviously, if you know how the reaction happens, it is simpler for you to understand what are the products and substrates. If you just mug up what is the substrate, what is the reactant, that will be difficult. If you understand how it happens, you will have some, you will be easily finding it out and writing in the exam. And in the inorganic part, yeah, I do agree we have to remember some data. Like we do have a lot of exceptions in inorganic part. We have to remember that can be achieved if you read the NCRTs after covering all the discussions. You be thorough with the NCRTs many times, at least 3 to 4 times. So then only you will be getting command over the subject. For physical chemistry part, Lakshmikant, we need to practice a lot of examples, lot of models. Okay, that is what we are going to do in your respective topics, like in the organic or physical or inorganic. You just don't need to worry with the past, what happened. You just to try to focus on the present and try to work hard, and ultimately you will be reaching your respective goals. Am I clear?
Yes, sir.
Yes. So, okay, fine. That's enough for the introduction day. So, without wasting any other time, we'll start with the discussion. So, today we are going to start with the chapter named D and F blocks, because these D and F block elements, they stand as a foundation to understand the coordination compounds as well, right? Let us try to understand this chapter, students. D block and F block. So we are going to looking at these properties like general characteristics, electronic configuration, atomic radii, magnetic properties, and formation of interstitial compounds. All these things we are going to study. And of course, ionization energies, oxidation states, alloy formations, catalytic properties, all the other things also we are going to looking at subsequently. Let us now first understand what is the position of D block element. So if you look carefully at the periodic table, you have S block here. In the S block, we have group 1 and 2. And then you have P block. Of course, the transition I have neglected out. Why means you will get the clarity. I'm talking about the period 1. Like if you take the period 1 or period 2, you will be having only S and P subshells are going to be filled. So if you look carefully, hydrogen we place separately at the center of the periodic table. We do have helium then. After hydrogen and helium, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And then you have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Why I am writing these elements? Although we are studying D block elements, I have not written the D block element first. Because you need to know in which period the D subshell is going to be filled. Yes or no? So this is going to be of period 1, where you have helium alone. And anyone knew why hydrogen is separately placed at the center of the periodic table? Hydrogen shows similarities. Write down the students. Hydrogen shows similarities with the group 1 as well as group 17. Since the electronic configuration of hydrogen is 1s1, it is similar to that of alkali metals, like it can lose one electron easily. That is why it has some, sorry, listen carefully. Hydrogen, yeah, hydrogen has electronic configuration of what? Hydrogen has how many electrons? Hydrogen has one electron. Because of that one electron is supposed to be filled in the lowest energy subshell. So 1s subshell, we have 1s, then 2s, 2p, then you have 3s, 3p, 3d, 4s, 4p, 4d, 4f. Like that you have filling. The energy of subshell is directly proportional to n plus L value. What is the n value? N here stands for? What do you mean by n here? The energy of the
quantum number.
Very good. The energy of the subshell is directly proportional to n plus L value. N stands for principal quantum number. What does L stands for?
Azimuthal quantum number.
Azimuthal quantum number. So for 1s, you try to calculate n plus L value. What is the value of n for 1s?
1.
1. For S subshell, what is the value of L?
0.
0.
0. Very good. So what is the value of n plus L?
1.
1 plus 0, that would be 1 plus 0, that would be 1. Try to calculate for 2s. Obviously, n value is equal to 2. N value is equals to 2. L is equals to 0. For S subshell, L is equal to 0. For P subshell, L is equal to 1. For D subshell, L is equal to 2. For F subshell, L is equal to 3. L values. For S subshell, L is equal to 0. For P subshell, L is equal to 1. For D subshell, L is equals to 2. For F subshell, L is equal to 3. So if you try to look at the calculation of n plus L for 1s subshell, you have only value of 1. For 2s or 2p or 3s or 3p or 3d or any other higher subshell you figure out, what is the n plus L value? It will be greater than 1 or not? Yes or no?
Greater than 1.
Yes, sir.
Yeah.
Greater than 1.
Where is the n plus L value minimum? The minimum n plus L value is for 1s subshell. whenever we have minimum n plus L value, the energy of that subshell is minimum. Electrons are arranged in the orbitals or in the subshells in such a way such that the lowest energy subshell is completely filled first. I repeat this, listen carefully. Whenever you are filling electrons, the electrons are filled in such a way such that lowest energy subshell has to be completely filled first. Which is the lowest energy subshell based on this n plus L value? 1s. So 1s has to be filled first. So how many electrons are there in hydrogen? We have 1 electron. So that 1 electron has to be placed in 1s. So electronic configuration of hydrogen is 1s1. Hydrogen has electronic configuration of 1s1. You consider group 1 elements like lithium, 3, 1s2, 2s1. Sodium, 1s2, 2s2, 2p6, 3s1. Similarly, you consider group 17 elements like fluorine, 1s2, 2s2, 2p5. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. You know how to write this electronic configuration, students? If you don't know, I'll explain, listen carefully. So after filling 1s, you have to fill the next higher energy subshell, which is going to be a 2s. After filling 2s, the next higher energy will be for 2p. So you have to fill 2p. After filling 2p, in the 2p, how many orbitals are there? 2p is a subshell. In the p subshell, we have px, py, and pz. 3 atomic orbitals are there. Every atomic orbital can have 2 electrons. So 2px can have 2 electrons. 2py can have 2 electrons. 2pz can also have 2 electrons. So how many electrons can be there in total? 2 plus 2 plus 2. 6 electrons. That's why in the 2p, yeah, very good. That's why in the 2p subshell, I am writing 6 electrons. This 2p is a subshell. It is not atomic orbital. 2px, 2py, 2pz, they are atomic orbitals, right? After filling 2p, you try to figure out the n plus L value for 3s. 2p and 3s. You try to figure out n plus L values. For 2p, what is the value of n plus L? For 2p, what is the value of n? What is the value of n?
2.
2 plus 1. That would be 3. What about 3s?
3 plus 0 equal to 3.
3 plus 0.
3.
Very good. So whenever the n plus L value is same, then which is having higher energy among 2p and 3s?
3.
So based on the principal
2p.
quantity.
Yeah, when the n plus L value is same, greater the value of n, greater is the energy. Which has higher n? 3s.
3s.
So that is why 3s has higher energy. 3s has higher energy means 2p should be having lower energy. If 2p has lower energy, first 2p is going to be filled, not 3s. So that's why after 2s, I have filled 2p. After 2p, I have filled 3s. After 3s, I have to fill 3p. Then you have filled 4s, then 3d. Like that, the configuration goes on. Now, based on these n plus L values, I have written the electronic configurations of lithium. 1s2, 2s1, 3 electrons I have to fill. Sodium, 11 electrons I have to fill. 1s2, 2s2, 2p6, 3s1. Similarly, fluorine and chlorine, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6, 3s2, 3p5. Are these configurations clear or not?
Yes, sir.
Yes, right?
Yes, sir.
Yes.
Now the question. Hydrogen shows similarities with group 1 and group 17. You need to understand why. In the group 1, if you look at, 1s2, 2s1. The second shell is the outermost shell for lithium. Yes or no? For lithium, you have nucleus at the center of an atom. You have first shell, you have second shell. In the first shell, you have 2 electrons filled. In the second shell, you have 1 electron filled. Second shell is the outermost shell. Lithium can lose this electron to get Li plus ion. Lithium has electronic configuration of 1s2, 2s1. If it loses 1 electron, what will be the electronic configuration of Li plus?
1s2.
1s2.
Very good. 1s2 and the electron is lost. And obviously, you are saying lithium can lose the electron and get the electronic configuration of 1s2 means you are indirectly saying that the electron is lost from the outermost shell. It cannot be lost from the inner shells. Why? Because the inner shell electron is close to nucleus. Because of that, nucleus attraction is greater. So the inner shell electron cannot be lost. The outermost electron that has been lost, Li plus has 1s2 configuration and electron is lost. Among 1s2, 2s1 and 1s2, which is more stable? Among 1s2, 2s1 and 1s2?
1s2.
1s2? Yes or no? Completely filled subshell. So 1s2 is going to be more stable. What do you mean by that? That means lithium has more tendency to form Li plus ion or not? I can say that because lithium is converting into Li plus. If you try to write the electronic configurations of lithium and Li plus, you can see that Li plus has a more stable configuration. So the conversion of lithium to Li plus is easy. Conversion of lithium to Li plus is easy. Similarly, you think of sodium, students. Sodium, it has 1s2, 2s2, 2p6, 3s1. Can it lose an electron to form Na plus?
Yes.
Yes. It can also lose an electron, and the electron has to be lost from the outermost shell only. So sodium, whenever it loses the electron, it gets 1s2, 2s2, 2p6 electronic configuration, which is stable. Can I say group 1 elements have a tendency to lose an electron to get to their respective ions or not?
Yes,
or
sir.
no?
Yes, sir.
So when I talk about group 1 elements, the group 1 elements has some tendency to lose 1 electron to form ions in their +1 states. Why? Because the ions in their +1 states are more stable. Because the ions in their +1 state are more stable. Similarly, can hydrogen lose an electron? Hydrogen also has only one electron. 1 electron in the outermost shell, similar to that of group 1. In all the group 1 elements, you have 1 electron in the outermost shell. Hydrogen, can it lose that electron? 1 electron, similar to that. Because of, yes, what is the first point we can say is, because of 1 electron in the outermost shell, the hydrogen also has some similarity in the electronic configurations of group 1 elements. When the electronic configurations are similar, the properties are going to be similar. Write down that point. Because of 1 electron in the outermost shell, hydrogen shows some similarity with the alkali metal. Alkali metals means group 1 elements. Alkali metals means group 1 elements. Now look at the same hydrogen and compare them with group 17. Now the comparison is with group 1, right? You compare now with group 17. Like I have written the electronic configuration of fluorine. I have written the electronic configuration of fluorine. You let us write fluorine takes an electron. What happens whenever fluorine takes an electron? You get F minus. fluoride ion because electron is added. Negatively charged particle is added means you get more negative charge. What is the electronic configuration of F minus? Anyone?
1s2, 2s2, 2p6.
Very good. 1s2, 2s2, 2p6. Fluorine we have already done. 1s2, 2s2, 2p5. Which is more stable?
F minus.
F minus.
Minus, right? So the group 17 elements, they have a tendency to gain an electron to get to the nearest inert gas configuration. Similarly, Cl minus is also more stable. F minus, Cl minus are stabilized because they are going to have electronic configuration similar to that of inert gases. Similarly, look at hydrogen now. Hydrogen, can it gain an electron? If hydrogen gains one more electron, what you will get?
1s2.
1s2. That means same configuration as helium. So because hydrogen also has a tendency to gain that electron and to form helium, and group 17 elements also have the same tendency to gain an electron and form respective inert gases. So can I say hydrogen shows similarities with group 17 also? Yes or no?
Yes, sir.
Yes, no?
Yes,
So
sir.
yes, sir. Very good. With the group 1, hydrogen shows similarity because the outermost electron is only one, which can be removed. With the group 17 also, hydrogen shows similarity because it can also gain an electron and convert to inert gases. That means hydrogen is showing similarities with the group 1 and group 17. So then where I have to place it? Either in group 1 or in group 17. Both are conflicts. If you are very good to be placed in two sections, yes or no? So then the conflict arises. So where to place you? So obviously the same scenario appears here. The whole reason for the placement of element in a particular group is the element in that group will be showing similarities with the other elements of the group. But hydrogen is showing similarities with group 1 and group 17. Because of this, the position of hydrogen is an issue, and that is why it has been placed at the center of the periodic table. It is not placed above lithium directly. It is placed at the center of the periodic table. Understood now, students?
Yes, sir.
Yes?
Yes,
Very good.
sir.
So hydrogen is placed at the center of the periodic table. We have next helium. And then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So these all belongs to which period? Lithium to neon period?
Second period.
Second period, very good. Third period you write down sodium, magnesium, aluminium, silicon, so on up to argon. These all belong to third period. And then comes the fourth period. Then comes the fourth period. Like in the fourth period you have potassium, calcium, so on up to after argon you have krypton. Yes or no? Now before writing the electronic configurations, let us try to understand how to write the electronic configuration of nitrogen, let us say. Not writing like 1s2, 2s2, 2p3. Understand how we are filling the electrons. Listen carefully. Let me take it in. Okay. We have not entered the D block yet. We are understanding where the D block lies. So if you are trying to fill, let me draw this periodic table, just a broad picture again. We have sodium, nitrogen somewhere here, lithium, beryllium, boron, carbon, nitrogen, and you have helium somewhere above. If I want to write the electronic configuration of first beryllium, if I want to write, how I am going to write, students? If I want to write the electronic configuration of beryllium. Yes, Harishri, any doubt?
No, sir.
No, right? Okay, fine. So if I want to write the electronic configuration of beryllium, how I am going to write? I will say that one way is I can write 1s2, 2s2. Other way is I can write helium. I am going to fill the electrons up to helium, right? That is the inert gas in the above period. After helium, you are going to fill the, this is the second period, so you have to fill the 2s, because it's an S block element, you have to fill in the 2s only. Period 2, that is why 2, it is an S block element, so that is why S subshell. And how many electrons I have to be filled? 2 electrons, because it is a group 2 or alkaline metal. Listen carefully how I have written. Beryllium electronic configuration is neon. What is neon? Neon is the inert gas in the previous period. After neon, I am filling electrons in the second shell. Why? Because beryllium belongs to period 2 and beryllium is a S block. That is why I have to fill electrons in the S subshell only. And how many electrons I have to fill? 2 electrons. Why? Because it is a group 2. Because it is a group 2. Can you write what about the electronic configuration of magnesium in the same manner? After beryllium, you have magnesium, right? Can anyone say how to start?
Sir, argon 3s2.
Argon.
Neon.
Neon.
Neon, right?
Yeah,
Neon.
Neon.
Yes, sir. After helium, you have neon. After helium, you have argon. So neon, you are going to fill. What is neon? The inert gas electronic, the inert gas in the above period. Magnesium belongs to period 3, so you have to fill the third shell. And it is an S block element, so you have to fill the S subshell. It is a group 2 metal, so you have to fill 2 electrons. Right? Very good. Simple. Now in the same way, try to write the electronic configuration of nitrogen. Nitrogen. Nitrogen, how it is obtained? First, I can write the inert gas in the above period. Nitrogen is in the period 2. What is the inert gas in the period 1?
Helium.
Helium. Very good.
Helium.
Yeah, very good. After filling helium, where am I filling the electrons? After filling helium, to approach neon, I am coming in this direction. That means I have to fill the S subshell. In the P subshell, I have to fill 2 electrons. And then only I appear to nitrogen. Yes or no? So after filling the inert gas in the previous period, I have to fill electrons in the, obviously nitrogen belong to second period, so I have to fill electrons in the 2. S subshell I have to completely fill. Then only I can fill the P subshell. So 2s I have to completely fill 2s2. After filling 2s completely, I have to go with the 2p. In the 2p, I have to fill how many electrons? Boron means 1 electron, carbon means 2 electron, nitrogen means
3 electrons.
3 electrons. So helium 2s2, 2p3, that is the correct electronic configuration. Write down the electronic configuration for phosphorus. Write down, students. Anyone say it out?
Neon 3s2, 3p3.
Neon 3s2, 3p3. Very good. Can anyone say for arsenic? Nitrogen, phosphorus, arsenic, antimony, bismuth.
Argon 4s2, 4p3.
Argon 4s2, 4p3. Anyone else can say the electronic configuration of arsenic?
So arsenic is argon 3d10 4s2 4p3.
Yeah, very good. Arsenic is argon 3d10. You look at where argon is. Nitrogen, phosphorus. You look at where arsenic is. Nitrogen, phosphorus, arsenic. It is in the period 4. In the period 4, if you want to reach arsenic, we have to fill the inert gas in the previous period. Then you have to fill the S subshell. And then you have to fill the D subshell. And then only you are entering the P subshell. That means the heavier p block elements, to write the electronic configuration, I need to fill the s subshell, then d subshell, but this d subshell is the nd or n minus 1d? 3d means fourth subshell is the outermost subshell. 4 minus 1, yes or no? 4 minus 1 is 3, so it is n minus 1d subshell. If we have nucleus, first shell, second shell, third shell, fourth shell, whenever you are trying to fill electronic configuration for arsenic, you have to fill 3d and then you have to fill 4p. You will be filling 4s first. S subshell is filled first. Then you are going to fill 3d. Then you will enter for 4p. Yes or no? That means in the heavier p block elements, you will see that the inner, this is the inner shell or not? 3d lies in the third shell. Fourth shell is the outermost shell, means third shell is inner shell. Yes or no? In the d block elements, in the d block, you are going to have the 3d series filled, the 4d series filled, the 5d filled, and the 6d filled. Listen carefully. The 3d series, the 4d series, the 5d series, the 6d series, all of these corresponds to your d block elements. What are d block elements? D block elements are those elements where electrons are filled in the 3d subshell or 4d subshell or 5d subshell or 6d subshell. Because of these d block elements, the heavier p block elements electronic configuration is going to be affected. Understood this point or not, all of you?
Sir, can you repeat?
I am repeating, listen carefully. So if you write the electronic configuration for nitrogen, you have simply written neon 2s2 2p3, because nitrogen, how it is obtained? After helium, you are filling 2 electrons in the s subshell, then you are filling 3 in the p subshell, right? For phosphorus, how we are adding the electrons? Neon, then s subshell 3s2, then you are filling electrons in the p subshell. Up to that, is that clear or not? Nitrogen, phosphorus.
Yes, sir.
Yes, sir.
Now when you try to write electronic configuration of arsenic, you should not write just 4s2, you should not write just 4s2 4p3, because you are missing out the 3d subshell. Here we have 3d subshell where the elements are there from scandium to zinc. So to reach arsenic, you have to first fill argon, argon done. Then you have to fill what? The s subshell, 4s subshell has to be filled, 4s has to be filled. After 4s, you have to fill 3d or not? Because we have the d block, right? You have the d block or not? So
Yes,
after
sir.
4s,
Yes, sir.
you have to fill 3d. Then only you are reaching the arsenic by filling 4p. That means actually you are writing arsenic electronic configuration as argon 4s2, because you have filled 4 subshell. Period 4, 4s you have to fill. After 4s you are filling 3d10. The d subshell you have filled n minus 1d. After filling electrons in n minus 1d, you enter in the np. So n minus 1d, these subshells are going to be filled when you try to write the electronic configurations of heavier p block elements. Is that clear?
Yes, sir.
Yes. Now what we are looking at?
Yes, sir.
Now what we are looking at is not the p block. Our interest lies in the d block. So in the fourth period, which d subshell is filled? I am talking about fourth period. No, arsenic belongs to fourth period. So in the fourth period, which d subshell is filled? Fourth period. In the
3D.
3d. In the fifth period,
4D.
4d. In the sixth period,
5D.
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 In the seventh period, you have 6d. Right? So the fourth period is also called as 3d series. The fourth period d block elements The fourth period D block elements, they are also called as 3D series elements. Fifth period D block elements, they are also called as 4D series elements. Sixth period D block elements, they are also called as 5D series. Seventh period D block elements, they are also called as 6D series. That is what we are going to see now. Yeah, look at this 3D series. 3D series means you are having electrons filled from scandium to zinc. That means you are filling 3D and you are getting elements from scandium to zinc. You look at this, students. In the 3D series, you have electrons filled from 3D1 to 3D10. You have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These elements are also called as 3D series elements. Next, you have 4D series from yttrium to cadmium. This 4D series belongs to which period? Fifth period. 3D series belongs to fourth period. In the fourth period and fifth period, we have only the D subshell filled. But if you go with the 5D series, like from lanthanum to mercury, if you look carefully, after lanthanum, what you are having? Lanthanum is, what is the electronic configuration of lanthanum or atomic number? How much it is? 50?
57.
57. After lanthanum, you are having electronic configuration or atomic number of 72. That is hafnium you are having. What happened to this 58 to 71? Lanthanides, very good. So 58 to 71, they are lanthanides, where the 4F subshell is filled. Similarly, in the 6D series, you have actinium, then you got rutherfordium. So you are missing 90 to 103. So those elements are said to be actinoids. So 5D series is lanthanum and hafnium to mercury. 6D series is actinium and rutherfordium to copernicium. You should not write like lanthanum to mercury. This is wrong. Lanthanum and hafnium to mercury. These are all 5D series elements. Actinium and rutherfordium to copernicium. This is your 6D series. What about your 58 to 71? 58 to 71, that is your lanthanoids. 90 to 103, that is your actinoids. These
Actinoids.
two are placed separately at the bottom of the periodic table and they call your F block. Understood now what is D block elements? D block elements consists of 4 series: 3D series, 4D series, 5D series, and 6D series. 3D series means 4th block, 4D means 5th block, 5D means 6th block, 6th period, 3D means 4th period, 3D means 4th period, 4D means 5th period, 5D means 6th period, 6D means 7th period. In the 6th period, you will be having lanthanum and hafnium to mercury. In the 7th period, you will be having actinium and rutherfordium to copernicium. In the 6th and 7th period, you will be having lanthanoids and actinoids, but these lanthanoids and actinoids were placed separately at the bottom of the periodic table. Is that clear, students? That is nothing but your D block and F block position in the periodic table. Just basic introduction. Clear or not?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Yes,
Yes, sir.
very good. Now we need to understand what are D block elements, what are the different terminologies involved, what is their electronic configurations, how the electronic configuration of D block is going to be affecting their properties. The first point you need to understand is the 40 D block elements are present, and all these D block elements If you look carefully, you are going to have S block here. You are going to have P block here afterwards. And you will be having F block at the bottom. Like this lanthanum to hafnium, you have elements, right? Like 58 to 71. They were placed in the lanthanoids. And actinium to ruthenium, between those the elements are there, they are placed in the bottom, like F block, like actinoids. Now look carefully. If you look at these D block elements and try to write their electronic configuration and understand their position in the periodic table, you have first S block and then you have P block. In between the S block and P block, what do we have? D block.
D block.
And this F block is placed separately at the bottom of the periodic table. Because the D block is lying between S block and P block, can I say the D block elements as transition elements?
Yes, sir.
Yes. Write down
Yes,
the
sir.
point. Yeah, write down. D block elements. First listen carefully and then note down. D block elements, they are lying in between S block and P block. That means they are transitioned between S block and P block. That is why the initial name has been given to that as a transition elements. Also, they mean that the properties of D blocks are transitioned between S block and P block. If you look at S block, mainly you have metals or non-metals. S block,
Metals.
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 Metals,
If you look at P block, you have
non-metals,
metalloids also there,
Non-metals.
non-metals also.
non-metals.
So D block you will have metals, and the properties of these D block elements, they are going to be transitions between S block and P block, right? So D block elements, we do have exception. D block elements are transitioned between S and P block, and that is why they are also called as transition elements, transition metals or transition elements. But first you need to understand one more point. Does this 12th period, like D block means we will have third group, fourth group, fifth group, so on up to 12th group, right? In the 12th group, you have zinc, cadmium, mercury, and copper, nickel. Are they called as transition elements?
No, sir.
Nandana, why?
Sir, in their like ionized form, they did not lose electrons from the D block. They lose from 4s, and
Yeah,
they are
very good.
fully orbital.
Very good. So what is the initial idea? Initial idea is very basic. Since they are present in between S block and P block, they are called as transition elements. But this is wrong. This definition is not valid. The correct definition of transition elements is the element should have at least one electron, one unpaired electron in the D subshell, either in the ground state or in its oxidation states. But the correct definition of transition elements is transition elements is the element should have at least one electron, one unpaired electron in the D subshell, in a ground state, or in the excited state, or in its oxidation state, possible oxidation states. Write down this, very important. Possible oxidation state. So if you try to write the electronic configuration of scandium, you will have argon. After argon, because scandium before that, this is belonging to fourth period. In the period 3, you have argon filled, that is the nearest inert gas. After argon, you have to fill the 2 electrons in the S subshell, so 4s2. Then you are filling 3d, so 3d1. So on fill titanium, you will get what? Argon 4s2, 3d2. Vanadium, argon 4s2, 3d3. Chromium, what is the electronic configuration? Argon, chromium 4s2, 3d4 or 4s1, 3d5.
4s1 3d5.
4s1, 3d5, because 3d subshell is going to be half filled here. Half filled electronic configurations are more stable. Like that, you try to write the electronic configurations, because electronic configurations itself gives idea about the chemical properties. If I talk about any chemical property, I need to know the electronic configuration alone. Okay, that is a major point. First, write and understand the electronic configurations carefully. Manganese, argon 4s2, 3d5. Here you have exception for chromium. After manganese, you have iron, argon 4s2, 3d6. Cobalt, argon 4s2, 3d7. Nickel, argon 4s2, 3d8. Copper, argon 4s2, 3d9 or 4s1, 3d10. Copper.
So 3d10.
4s1 3d10.
4s1 3d10.
3d10.
Very good. And then finally zinc, argon 4s2, 3d10. Now look at all the elements from scandium to zinc and their electronic configuration. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, everywhere you have an unpaired electron or not. 3d5 means unpaired electron is there, because you have to follow Hund's rule, no? You have 5 d orbitals. 3d1 means you will fill 1 electron. 3d2 means you will fill 2 electrons in 2 different subshells, in 2 different d orbitals of the same subshell. d3, 1 more electron in the other d orbital. d4, d5, d6, d7, d8. So everywhere d1, d2, d3, d5, d6, d7, d8, all these will have unpaired electrons or not, up to d8. Yes or no, students? Like,
Yes, sir.
yes or no, students? If you try to write d1, how many unpaired electrons are there? d1 means d1 means how many unpaired electrons are there? Only 1 unpaired electron.
1 unpaired
One.
electron.
d2,
2 unpaired.
3 unpaired.
2 unpaired. d3,
3
3.
unpaired.
Three
d4, 4.
unpaired electrons.
Yeah, d5, 5. d6,
4 unpaired electrons.
4
unpaired.
unpaired.
Very good. d7,
3.
3
d8.
unpaired electrons. 3 unpaired, 2 electrons.
So d1 to d8, yeah, d1 to d8, all of you are saying there are unpaired electrons. For if you look at a copper, you have d10. If you look at zinc, you have d10. For copper, you have d10, but copper can exist in Cu plus 2 forms. Write down Cu plus electronic configuration. Argon is same. Cu plus, how it is obtained?
So
Argon
1 electron
3d10.
from 4s is lost.
Argon 3d10.
Yeah, argon 3d10. Cu plus 2 is argon
3d9.
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 So read the configuration. The correct definition of transition elements is the element should have at least 1 unpaired electron in the d subshell, in a ground state, or in it. Yeah, the element should have at least 1 unpaired electron in the ground states or in its possible oxidation states. copper can exist in Cu plus and Cu plus 2. In the copper plus 2, you have 3d9. When you have d9, how many unpaired electrons are there? d9.
1.
1
One
unpaired.
unpaired. So we still have unpaired electron for copper. So since unpaired electron is present in the copper in the plus 2 stage, so can I call it as a transition elements or not?
Yes, sir.
Yes,
Yes,
it is
sir.
a transition element. But what about group 12? You have zinc. Zinc can exist in Zn plus or Zn plus 2. If you write Zn plus 2, you will have argon 3d10. Argon 3d10 is the electronic configuration where you do not have any unpaired electron. That means only the group 2, group 12 elements do not have unpaired electrons in the d subshell. That is why only group 12 are not called as transition elements. Remaining all other groups, they are called as transition elements. Understood this point or not? Clearly.
Yes, sir.
Yes, sir.
Yes. So from scandium to zinc, if you look at, you will be having unpaired electrons except zinc. That is why all the other elements, they are said to be transition elements, whereas the group 12 elements, they are not transition elements. But still, we study the group 12 element properties along with the other groups only. We can't separately study the group 12 elements. Although they are not called as transition elements, we study them combinedly with combinedly with the transition elements. Sir, you are saying a lot of things regarding unpaired electrons. What are these unpaired electrons going to do? That is the first question you should ask yourself or myself. What is the question? Sir, you are saying a lot of things. You have defined transition elements. We have defined transition metals are those metals which have an unpaired electron in the d subshell. Everything fine. But why you are stressing out on these unpaired electrons? What is the role of this unpaired electron? The role of this unpaired electron is the number of unpaired electrons, they are going to be deciding the metallic bonding. The first point, understand carefully. The unpaired electrons, they are going to be deciding the metallic bonding. You know covalent bond, you know ionic bond, you know coordinate covalent bond. Similarly, we have a metallic bond. The metallic bonding is decided by this unpaired electron. I'll just give the idea to you. The number of unpaired electron gives the metallic bonding. Information regarding metallic bonding. If a metallic bonding is strong, metals are strongly attached. So enthalpy of atomization is decided or not? Enthalpy of atomization. If enthalpy of atomization is decided, based on that we can decide the electrode potentials. Relate the students. Enthalpy of atomizations, electrode potentials, and metallic bonding and ionization energies, all these are related to the electronic configurations only. What I'm saying, the electronic configuration and the number of unpaired electrons gives us an idea regarding metallic bonding, electrode potentials, enthalpy of atomizations, and a lot more things. That is the idea. That is a simple statement. But how? You will be asking, sir, how you can say metallic bonding based on this? How you can comment on atomization, enthalpy of atomization based on this? To understand that, we need to know what a metal is and what is metallic bonding first. Is everything clear so far? So what's the difference between transition elements and group 12? Yes or no?
Yes, sir.
Yes, sir.
Yes, no?
sir.
Very good. Very good. Now we are going to decide what is metallic bonding and what is the effect of unpaired electrons on metallic bonding. Can anyone define what is a metallic bonding, students? Okay, fine. No need to worry. Simple discussion only. I have take some metal rod, like imagine this as an iron rod. you might be coming across a lot of iron rods when you are near to the building constructions and all. Yes or no? Iron rod is a metal, right?
Yes,
So
sir.
in a metal, you might have studied in solid state. We have to relate some points of solid state to this. We do have some definition like crystal sites or crystal lattice. Yes or no? Crystal sites or lattice points are those points where the constituent elements of the solid are present. What is that? Lattice sites, lattice points are those points where constituent particles are present. You know this or not?
Yes, sir.
If you don't know also, no need to worry. That is a thing. Like that is a basic definition only. Lattice points means what? Lattice points means they are the points in space where the constituent particles are present. As said, constituent particles. If I talk of a solid like NaCl, NaCl is a common salt. Like what do we have in NaCl? We have Na plus ion and Cl minus ion. What are the constituent particles? Like you might have seen the common salt, right, students? In the common salt, like NaCl, we have Na plus and Cl minus ions. So if you look at the structure of NaCl, at the lattice sites, we have ions present. What do we have? NaCl is solid. You might have seen while you are using it in the daily day-to-day life. You might be seeing the table salt. It is a crystalline solid or not? So in that crystalline solid,
Yes, sir.
constituent particles are ions. Like I am now talking about metallic solid, like iron rod. In the iron rod, what are the constituent particles? The metal kernels. What is a metal kernel? We'll understand that. So we have a metallic element, like a metal M is there. Let us say some N valence electrons are there. So those valence electrons are removed from the metal. So metal M is generating Mn plus ions and N electrons are released. Like if I take Fe, Fe is giving out Fe plus 2 and 2 electrons are lost out. What is Fe? Your metal. What is Fe plus 2? What is Fe plus 2? Its respective ion, it is said to be metal kernel. Write down this, metal kernel. Kernel means core. Kernel means what? Core. Like you have an atom, right? In an atom, you have nucleus. You have first shell, second shell, third shell, and let us say outermost shell is a fourth shell. Let us say one electron is there in the outermost shell. If you remove this one electron, what you are left out with? The inner electrons only, the core shells only. Yes or no? If outermost electrons are lost, whatever the left out part, that is nothing but the core. The other name is kernel. The other name is kernel. Metal kernel means what? It is the species obtained by losing the outermost electrons. Like Na is there. Na, if it loses Na plus, Na if it loses an electron, it gets Na plus. What is Na plus? It is a metal kernel. Kernel means core. Understood this point or not? Kernel means core. Got this point? Metal will be losing electrons to give metal kernels. Just a different name. You can say ions also. But the same metal elements are going to be present. So if these electrons are lost from the outermost shell, you are going to generate metal kernels. Is that point clear?
Yes, sir.
Yes, sir.
Yes. Now,
Yes.
very good. Now, in the metallic bond or in the metallic structure, what do we have is at every lattice site, you will have metal kernel. What are these? Metal kernels like Mn plus, Mn plus, Mn plus, Mn plus. These are all lattice sites. Mn plus, Mn plus. At every lattice site, you have metal kernels. Mn plus, Mn plus. Metal M in the N plus state. You may ask a question, sir, what happened to the lost electrons? Why are you not writing the electrons? The electrons are there. Yes, I cannot remove the electrons. Where are the electrons now, students? They are moving throughout the metal. So what is a metal? Like if you talk of a metal like Na, sodium metal, or iron rod, or copper rod, whatever the metal you say, you will be having metal kernels at lattice sites. What do you have? You have metal kernels at all the lattice sites. What about the electrons? Electrons are freely moving throughout the metal lattice. What about these electrons? Electrons are freely moving throughout the metal lattice. If I take iron, how many electrons are obtained, students? If I take one iron atom?
2
2
electrons.
electrons.
But in a metal, like in a metal rod, iron rod, how many iron atoms are there? Very high number or not? You will be having the number of iron atoms in a iron rod will be very, very high. Because 1 mole if you take, you will have Avogadro number. 1 mole means Avogadro number. 1 atom is giving 2 electrons. So Avogadro number will give how many electrons? 2 into Avogadro number. Very high number. Yes or no? That means how many electrons are moving throughout the metal? Very high. All these electrons are called as free electrons. In a metal, we always say there are free electrons in the metal. There are free electrons in the metal. Now I am explaining what is metallic bonding. Listen carefully. You have a lot of free electrons, very high number of free electrons. The electrostatic force of attraction between these free electrons and the metal kernel, that is nothing but your metallic bonding. What is metallic bond? Write down. Metallic bonding is the electrostatic force of attraction between one metal kernel and all the free electrons present in the metal. Present in the metal lattice. It is similar to your ionic bond, students. Ionic bond, let us say NaCl, sodium chloride, like table salt. In NaCl, we have electrostatic attractions between Na plus and Cl minus. The electrostatic force of attraction between Na plus and Cl minus, that is nothing but your ionic bond. Similar to that, the electrostatic force of attraction between one metal kernel and all the free electrons, that is nothing but your metallic bond. That is nothing but your metallic bond. Understood this point or not? What is metallic bonding? It is the electrostatic force of attraction between one metal kernel and all the free electrons present in the metal lattice. Understood this?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, I'll repeat it again. Listen carefully. What is metal kernel? You have a metal. From that metal, if you remove the outermost electrons, you are getting an ion, metal ion. The other name for the metal ion is nothing but metal kernel. The other name for metal ion is nothing but metal kernel. In the metal, you have metal kernels. That means these ions placed at different lattice sites. These are nothing but your lattice sites. At every lattice site, you have the metal kernel. The metal kernel, how it is obtained? By losing electrons from the metal. Where are the lost electrons? They are moving throughout the metal. They are nothing but your free electrons. Electrons are negatively charged or positively charged? Electrons are
Negatively charged.
Negatively charged.
negatively charged. Very good. Metal kernel Mn plus, is it positively charged or negatively charged? Mn plus,
Positively charged.
positively charged.
Positively charged.
How many electrons are there? Very high number of free electrons are there, because every metal is giving 2 electrons. If you take iron, how many free electrons are there? Very high number. All those electrons are attracted toward this metal ion or not, or metal kernel or not?
Yes.
Yes or no?
Yes, sir.
So all those electrons are attracted by this metal kernel. So that this attraction is just electrostatic attraction. There is no chemical bond. It is nothing but your electrostatic force of attraction. There is no overlapping of orbitals, nothing happened. The electrostatic force of attraction between all the free electrons and the metal kernel, that is nothing but your metallic bonding. That is nothing but your metallic bonding. Understood this?
Yes, sir.
Yeah, Prachi has a very good question. Sir, whatever the force between negative ion and electron. Negative ion, where is there, Prachi? For example, in NaCl. In NaCl, we don't have negative ions and electrons separately. Na is converting into Na plus electron. This electron lost by Na, that is gained by chlorine. Yes or no? The electron which is lost by sodium, that is actually gained by chlorine to form a Cl minus. So there is just Na plus and Cl minus. There are no electrons. So Na plus and Cl minus, they have attraction. Understood now? Okay. So in NaCl, we have sodium which is forming Na plus and one electron is lost. Whatever the electron lost by sodium, that is gained by chlorine to form chloride. So we have Na plus and Cl minus. There is some electrostatic attraction. That is nothing but your ionic bond. In metallic bond, similar to electrostatic force of attraction only, but the electrostatic force of attraction is between metal kernel and all the free electrons. Very, very logical point these are, not some basic stuff. Listen carefully. The metallic bonding is the electrostatic force of attraction between all the free electrons and the metal kernel. Now I am repeating this some 3 to 4 times I have repeated. Why? You may ask a question. Because to get you an idea that if we have more number of unpaired electrons, like if we have scandium, let us go with scandium. How many unpaired electrons are there? Argon, 4s2, 3d1. Then you have titanium, like we have written the electronic configurations, right? Yeah. Scandium, argon 4s2, 3d1. Titanium, argon 4s2, 3d2. Vanadium, argon 4s2, 3d2. If you have more number of unpaired electrons, then I can have more number of electrons lost. Like if you took off scandium, scandium can exist in +3 stage and it will release 3 electrons. If I have titanium, titanium can exist in +4 and +2 states. If you go on with manganese, manganese can exist in +7 stage because it can lose all its 5 unpaired electrons. Iron, it can exist in +2 or +3 states more stably. So with increase in number of unpaired electrons, what is actually increasing? The number of electrons lost, that is increasing or not? Yes or no? Look, listen carefully. From scandium to manganese, if I am coming, 3d1, 3d2, 3d3, 3d5, 3d5. What is happening to the unpaired electrons? From scandium to manganese, the unpaired electrons were increasing. Because of the unpaired electrons increase, we have stronger metallic bonding. If we have stronger metallic bonding, what do we have? Metal bonding is stronger, or electrons are attracting the metal kernel strongly. That means enthalpy of atomization. Enthalpy of atomization is difficult. What is enthalpy of atomization? Anyone say? The amount of energy required to remove one atom from the metal lattice to its atomic state. You have this is a metal iron rod. You have from the iron rod I want to remove one iron atom. In the iron rod you have very high number of iron atoms. If I want to remove one iron atom, how much energy I require? That is nothing but your enthalpy of atomization. If the iron rod has very strong metallic bonding, I require very high amount of energy to take out iron atom. Yes or no? If metallic bonding is stronger, very high amount of energy I have to provide to remove the electron. If metallic bonding is weaker, I can easily remove the electron. Are you understanding this point or not? Similar to your ionization energy. I repeat again, listen carefully. If a metallic bonding is stronger, is it easy to remove the atom from the metal lattice, or is it difficult to remove the atom from the metal lattice? Strong metallic bonding.
Difficult.
Very good. If metallic bonding is stronger, it is difficult to remove the atom from the metal lattice. This point you understood. When the metallic bonding is stronger, when you have very high number of unpaired electrons or low number of unpaired electrons?
High number of unpaired.
High number of unpaired electrons.
Very good, all of you. So how the unpaired electrons are changing? From scandium to manganese, unpaired electrons are increasing or decreasing?
Increasing.
Again, from manganese to copper or zinc, what happens?
Decreasing.
Decreasing. Very good. Yeah, that point you need to understand carefully. So what is actually happening here is, what actually happening here is, if I take enthalpy of atomizations, or if I take metallic bonding on the y-axis, delta HA I am writing enthalpy of atomizations, and on the x-axis I have 3D series elements. Although we have 3D, 4D, 5D, 6D, in our 12th standard we mainly focus on 3D series elements only, like 4th period elements only. So in the 3D series elements, if you try to concentrate from scandium to zinc, from scandium to manganese, unpaired electrons are increasing. So what happens from scandium to manganese? Enthalpy of atomization should increase. Then after, it should decrease. But there is an exception with manganese. Generally, what should happen, students? Enthalpy of atomization should increase. Then it should be decreasing. Look at, I am writing the 3D series elements. For 3D series, the enthalpy of atomizations should be increasing from the scandium to the middle, that means up to manganese, and then it should be decreasing. Why it is so? Because the number of unpaired electrons increases from the initial element to the middle elements, and then the number of unpaired electron decreases. But there is an exception for middle element like manganese. Why? Because manganese has a difficult or a different crystal structure. Different manganese technetium has different crystal structures. Like if you should say, like manganese will having very high number of unpaired electrons, so it should be obviously having very high enthalpy of atomization, but in reality it has somewhat less. The reason is the crystal structures are going to be different. This is for the 3D series. For a 3D series or 4D series or 5D series or 6D series, whatever the series you consider, the enthalpy of atomizations, they are going to be increasing from the first element to the middle of the series, and then they should be decreasing. The reason is the unpaired electrons increases from the first element to the middle of the series and then decreases. But for the middle elements, there is some exception. Why? Because they possess different crystal structure. Is that clear up? Everything?
Yes, sir.
Yes,
sir.
Yes. So this is a very logical point. Now, can anyone compare? Sir, okay, you are saying unpaired electrons has a greater role. Now we have understood that because of unpaired electron, metallic bonding is affected. Because of metallic bonding, enthalpy of atomizations are affected. If enthalpy of atomization is affected, electrode potentials are affected. If electrode potentials are affected, the oxidations and reductions are affected. So a lot of things are affecting, sir, because of unpaired electrons. That's completely fine. But let us try to compare the 3D series and 4D series metallic bonding. Which has a stronger metallic bonding, 3D series or 4D series? So metallic bonding, write down metallic bonding. Metallic bonding is directly proportional to enthalpy of atomization. Enthalpy of atomization. Can you say, if I am asking the question where the enthalpy of atomization is high for 3D or 4D or 5D, obviously I am indirectly asking you to look at the metallic bonding, where the metallic bonding is high. How you can say, students, where the metallic bonding is high? How can you say? Go with the definition. What is metallic bonding? Can anyone define? It is here on the board itself, screen. Can anyone define what is metallic bonding?
Electrostatic force of attraction between one kernel and electrons.
Very good. So if that metallic bonding is stronger, obviously enthalpy of atomization is stronger, yes or no?
Yes.
So for 3D and 4D, if I want to compare metallic bonding, I want to just compare which is going to lose the electrons easily. Because 3D series, metal kernel and electrons attraction, if I want to compare. 4D series also same, metal kernel has to produce and electrons will have attraction. 3D and 4D, if you try to compare, the 3D series element and 4D series element, which can easily lose an electron, the outermost electron?
4D series.
4D series.
4D series.
Very good. Because they are longer from the nucleus, right? The 4D series elements, they are farther from the nucleus, so they can be easily lost. If the 4D series elements can easily lose an electron, so metallic bonding would be high. If metallic bonding is high, enthalpy of atomization is high. So 4D series, if you want to write, I will be writing in the same manner. So some curve I will draw. But above 3D, the enthalpy of atomizations are going to be above 3D. Similarly for 5D, this is for 4D and this is for 5D. Okay, like this. For 3D, 4D, 5D, the metallic bonding is going to be increasing, or highest for 5D, then for 4D, then for 3D. Metallic bonding is directly proportional to enthalpy of atomization. That is why the higher series like 5D series can easily form the metal-metal bond. But the lower elements in the 3D series, I cannot write iron can form a bond with iron easily. One iron cannot form another bond with another iron atom easily because of least metallic bonding. But if you go with the heavier elements in the 5D series, in the 4D series, there the metal-metal bonds are easily formed. Right, students? So this is about your metallic bonding and enthalpy of atomizations, right? So let us now look at the general electronic configurations and a few exceptions. General electronic configuration is simple. We have already discussed this. Like we have written the electronic configuration from scandium to zinc also, right? So n-1d 1 to 10, ns 1 to 2. The n-1d stands for the inner d orbitals which may have 1 to 10 electrons. The n-1d stands for inner d orbitals which may have 1 to 10 electrons. The n stands for the outermost s orbital which may have 1 to 2 electrons, because ns subshell, s subshell will have only one s orbital. In the s orbital we can fill a maximum of only 2 electrons. That is why ns 1 to 2. In the d subshell we have how many d orbitals? D subshell How many d orbitals are there? In the d subshell, how many d orbitals are there?
5.
5 d orbitals. So every d orbital can have 2. So in total you can have a maximum of 10 electrons. That is why n minus 1 d 1 to 10. But we do have exceptions. Exceptions are important. Exceptions with respect to electronic configurations. The above generalization has several exceptions. The energy difference between n minus 1 d and ns orbitals is very little. You have n minus 1 d and you have ns, right? That means let us say we have 3d and 4s. N plus L value, try to figure out n plus L. 3d, what is the value of n plus L? 3 plus for d subshell, what's the value of L?
No.
2.
2. So n plus L will be 5. For 4s, you try to figure out n plus L. 4 plus
4.
0, that will be 4. Which has higher energy?
3D.
3d will have higher energy when compared to 4s. That is true. Which is greater, students, among 0.111 and 0.110? Which is greater?
First one 0.111.
0.111. 3d is having greater energy when compared to 4s, but the energy difference, that is very small. Like 0.111 is greater when compared to 0.11, but the how much it is greater, that if you look at, that is very small. Like how much it is greater? It is just greater by 0.001. The same thing here, 3d is greater when compared to 4s, that's true. But the difference in energy, if you think of, that is very low. Like here, 0.111 is greater when compared to 0.11 by just 0.001 time. Only greater by that amount. 3d is greater when compared to 4s, but the energy difference between n minus 1d and ns is very little. Because earlier we have written the electronic configuration for chromium. We said that argon 4s1 3d5 is the correct, and we have said that argon 4s2 3d4 is the wrong. And what was the reason we explained? We said that the 3d has half-filled electronic configuration, so that is why it is stabilized. Okay, fine, but from where the 4s electron is entering the 3d subshell? From where the 4s electron is getting the energy to go into the 3d subshell? That is also a point, right? If we have electrons in the 3d, like completely half-filled electronic configuration, it is stable, that's fine. But how the electron from the 4s is going into 3d first of all? If it goes to 3d, it is stabilized. That's a different scenario. Yes or no? If you went to the respective dream university, you are very good, fine and good, you are so happy. That's fine. But how you have to reach that? There is a step now. How the 4s electron has to reach the 3d subshell? If they are different in energy, 3d has higher energy when compared to 4s. Practically speaking, you should not go, because energy less in the 4s, so electron has to be in the 4s only. But the energy difference, if you look at, the energy difference is very small. The energy difference between n minus 1d and ns is very, very little. That's what you need to understand. It's not like electronic excitation you can't do anywhere. Like you write the electronic configuration of carbon, 1s2, 2s2, 2p2. Why can't you write the electronic configuration of carbon as 1s2, 2s1, 2p3 and say that 2p subshell has half-filled electronic configuration? Can I write like this? Because 2p here also half-filled, no? It is not possible, because 2s and 2p have not so negligible energy difference. For carbon, I have 6 electrons, 1s2, 2s2, 2p2. That is the electronic configuration. But I cannot write that carbon electronic configuration as 1s2, 2s1, 2p3, stating that 2p3 has half-filled. That is wrong. Because the electron, if it went to 2p, it is stabilized, that's fine. But from where the electron gets the energy to go into 2p? That is the point. If the energy difference between 4s and 3d is very, very small, then we can say electron can easily go. Understood this point or not, students?
Yes, sir.
Okay,
Yes,
the electron going into 3D is stabilized because it has half-filled electronic configuration. That's very good, fine. But why the electron has a tendency to go to 3D 5 is the energy difference between 3D and 4s, that is very less. And next point, exceptions. Why the exceptions are there? Because the first is energy difference between n-1d and ns is very less. Second is half-filled and completely filled set of orbitals are relatively more stable. This point, second point, did you understand? Half-filled and completely filled orbitals are more stable.
Yes, sir.
Yes. Why, Hina? Why half-filled and
So it's
completely filled?
because, yes, sir, because they attain more noble gas-like configuration, and therefore it's harder for them to change the
No.
configuration either too.
Okay, very good. You forget about completely filled now. In the case of completely filled, you can say that they are similar to noble gas, so that is why they can be more stabilized. Now I am talking about half filled, like chromium only. You take example again. You are writing 4s1 3d5. The chromium is very far from the noble gas, right? In that series, krypton is very far away from chromium. So I cannot say that krypton is never similar to that of noble gas. So, but still I am saying that krypton has half filled and that is why it is stabilized. Why?
Sir, the exchange energy is lower in that case.
Very good. Because of symmetry and exchange energy.
Then Anjul will
Yeah. The reasons why half filled and a completely filled sets of orbitals are stable means because of symmetry and exchange energy. Write down these points. Why I am stressing out on this? Because it is useful to understand electronic configurations and ionization energies. Because of symmetry, you can say symmetry is there. Half filled means every d orbital get one electron, so it is symmetrical. Exchange energy means what? Exchange energy means, like if you say d5 configuration, you have one electron each in each d orbital. Let us give numbering 1, 2, 3, 4, 5. The first electron and second electron can exchange. First can exchange with third. First can exchange with fourth. First can exchange with fifth. 1, 2 can exchange. 1, 3 can exchange. 1, 4 can exchange. 1, 5 can exchange. Similarly, 2, 3 electrons can exchange. 2, 4 electrons can exchange. 2, 5 electrons can exchange. Third electron and fourth electron can exchange. Third electron and fifth electron can get exchanged. Fourth and fifth can also get exchanged. How many exchanges are there? First electron can exchange in 4 ways. Second electron can exchange in 3 ways. Third electron 2 ways. Fourth and fifth 1 way. 4 plus 3 plus 2 plus 1. How many? 4 plus 3 plus 2 plus 1.
10.
10 exchanges. So if you look at half-filled electronic configuration, every electron can exchange with the other electron in all these possibilities, like permutations or combinations, you can say. There are total of 10 exchanges possible. Because of more number of exchanges, more amount of energy is lost. That means stability gain. Okay, because of more number of exchanges, more energy, more exchange energy is lost. Exchange energy is lost, and thus, if energy is lost, the system will be stable or not. If you lose the energy, like early morning, you have breakfast, you have a lot of energy, you are moving here and there. Now you listen to 1.5 hour lecture continuously, you lost the energy. Yes or no? Imagine me only. I have done some breakfast and come to the lecture. I have spoken continuously for 1.5 hour. I lost energy. When compared to before class and after class, my energy has been reduced or not? Because I lost energy. Since I lost energy, I don't want to move here and there now. I want to be at stable position. So energy lost, stability gain. Lesser the energy, more is the stability. You can think of old man and a small kid. Small kid has a lot of energy. He moves here and there. He is not stable at all. Old man, less energy. He sits at a particular position. So because of exchanges, what happened? More amount of exchange energy is lost. Because of more loss of energy, what happened? And thus stability gain. What gain, students? Stability gain. Understood now? What is exchange energy? Because of exchanges of the electrons, whatever the amount of energy lost, that is nothing but your exchange energy. If more amount of energy is lost, system is stabilized more. So in the D5 configuration, we have more stability because of more exchange energy lost. Right? Is everything clear so far? We have discussed about what are D block elements, what is the position of D block elements first, what are transition elements, what is the exception of group 12 with that, and we have written the electronic configurations of 3D series elements. From the electronic configuration, we looked at the number of unpaired electrons. From the number of unpaired electrons, we commented on what type of metallic bonding it can result in. From that, we have resulted or seen again about the enthalpy of atomizations. And finally, we are about to proceed with the exceptional cases in the electronic configuration. Right? This is a discussion which we have done today. All of you should go through what I have been discussed in this day after the completion of the day. And if you have any doubts, you can ask me in the next class, or you can have my mobile number, WhatsApp number 79. All of you can note down my WhatsApp number, and you can ask your doubts to me directly. All of you note down my WhatsApp number, students. I'll write it in the comment section. You can take it out. Okay, fine. Just to go through and read these concepts again, and you will be getting even more clarity. Fine, students. Thank you all. Bye-bye.
Thank you, sir.
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 Thank you, sir.